While the Southern Optical Consortium released partial telemetry of interstellar comet 3I Atlas on October 18th, the Transient Object Coordinating Agency blocked peer review the following day, citing methodological inconsistencies without ever specifying them. 3 monitoring stations on different continents reported simultaneous calibration failures between October 14th and 16th while tracking a single object crossing the solar system at 91 kilometers per second. This is equivalent to 203,600 miles per hour, a speed 45% faster than the average for Kuiper Belt objects orbiting beyond Neptune. What could make 3 independent systems fail simultaneously when observing the same space rock? If you think comets are dirty snowballs following predictable orbits, the next few minutes will change your perspective. Leave your comment about what you think is happening, and subscribe to the channel to follow every development of this story. The object designated 3I Atlas was first detected on September 8, 2025, by the Automated Atlas System in Hawaii, the same one that identified comet Neowise in 2020. Its 3I nomenclature indicates the 3rd confirmed interstellar visitor, following Oumuamua in 2017 and 2I Borisov in 2019. But while Borisov behaved like a classical comet with a gas tail and a clean hyperbolic trajectory, 3I Atlas showed anomalies from the very first spectrum. Its trajectory placed it 1 astronomical units from the Sun in mid-October, just over twice Earth's distance from our star, approximately 315 million kilometers. For comparison, that's like being in the asteroid belt's orbit between Mars and Jupiter. A speed of 91 kilometers per second represents more than pure galactic escape velocity. Objects naturally originating from the Oort cloud or from nearby stellar systems like Alpha Centauri rarely exceed 60 kilometers per second when crossing the inner solar system. This 50% excess is not marginal. In terrestrial terms, it would be like observing a cargo truck moving at 180 kilometers per hour when the road limit is 120. You notice that. And 3 independent observatories noticed it at the same time, each reporting something their instruments couldn't process correctly. The Southern Optical Consortium operates a network of 2.5-meter telescopes in Chile and Argentina, specializing in high-precision photometry, basically measuring how much light an object reflects over time. The Andean Radio Observatory, installed at 4,200 meters altitude in the Peruvian Andes, monitors natural radio emissions from comets, those waves generated when solar wind ionizes gases escaping from the nucleus. Meanwhile, the Pacific Infrared Detection Institute, based in Mauna Kea, Hawaii, captures thermal signatures, the heat that every object radiates based on its internal temperature and the sunlight it absorbs. 3 completely different technologies, 3 simultaneous failures. Mariana Velasquez, calibration coordinator for the Southern Optical Consortium, stated in an internal memo leaked the following week that the CCD detectors showed saturation in specific pixels, even with neutral density filters activated, something she hadn't seen since a direct observation of Venus. In 2019, Dr. Hiroshi Nakamura, from the Radio Astronomy Group at the University of Tokyo, collaborating with the Andean Observatory, mentioned in an interview with the Astro News portal that the signal picked up was so narrow in frequency that their filtering algorithms initially discarded it as satellite interference until they realized it was moving with the comet. Natural comets 2.1 astronomical units from the Sun should maintain a stable core temperature, something between 190 and 195 degrees Celsius, with variations less than 5 degrees over several hours. Ice sublimation occurs gradually and uniformly at this distance. Partial data released by the consortium shows that 3I Atlas's thermal signature oscillated between 185 and 208 degrees Celsius in precise 37-minute cycles. This represents an amplitude of 23 degrees, nearly 5 times what was expected. Imagine your refrigerator fluctuating between 2 and 25 degrees every half hour. Something is rhythmically generating or dissipating heat. Preliminary calculations, based on its optical light curve, suggest that 3I Atlas is between 800 meters and 1.2 kilometers in diameter, roughly the size of 10 Maracana stadiums lined up. An object of this size, if it were an irregularly rotating rock, would produce brightness variations with periods of 4 to 12 hours, the pattern observed in 90% of known asteroids. 37-minute cycles imply either extremely rapid rotation or some internal process modulating thermal emission independently of rotation. The first option would tear a natural comet apart. The second has no precedent. Interstellar bodies follow hyperbolic paths, defined by the sun's gravity and the momentum they carry from outside. Once you know the initial position and velocity, you can predict the trajectory with error margins of a few kilometers over several weeks. The ephemeris software used by observatories worldwide, developed by NASA's Jet Propulsion Laboratory, does this with an accuracy of hundredths of an arcsecond, but 3I Atlas deviated. Measurements taken between October 10th and 18 reveal micrometric corrections of 0.09 degrees every 5.2 hours. Read that again. 0.09 degrees. That's 324 arcseconds, 3 times the apparent diameter of Jupiter as seen from Earth. 3I Atlas is correcting 45 times faster than natural objects. For an object traveling at 91 kilometers per second, a deviation of 0.09 degrees over 5.2 hours represents a trajectory adjustment of about 80 kilometers laterally. It's as if, every 5 hours, someone pushed the comet 80 kilometers sideways. Natural comets do this through asymmetric gas jets as the sun sublimates ice from their surface. But the optical and infrared spectra of 3I Atlas show no prominent tails or active plumes. Where's the gas needed to produce this thrust? Natural phenomena like pulsars, nebulae, and even comets produce signals around this frequency, but always with a bandwidth of tens to hundreds of hertz due to the thermal motion of the emitting atoms. The hotter the gas, the more dispersed the frequency. The signal detected from 3I Atlas has a bandwidth of only 0.28 hertz. That's 230 times narrower than any natural emission ever recorded from comets. This is 230 times narrower than any natural emission ever recorded from comets. Natural lasers exist in interstellar molecular clouds when specific conditions align atoms in population inversion, but they have never been observed in small objects like comets. The alternative is metallic cavity resonance, the principle that makes antennas and microwave ovens work. Space rocks do not have metallic cavities, or they shouldn't. If you take 3 independent anomalies, rhythmic thermal variation, trajectory corrections without visible jets, and ultra-coherent radio emission, and try to force them all to fit into known natural models, you need 3 separate coincidences happening on the same object at the same time. The probability of a natural comet exhibiting 37-minute thermal cycles is estimated at less than 1 in 5,000. The chance of trajectory deviations of this magnitude without detectable plumes is about 1 in 800. Radio emission with a bandwidth less than 0.5 hertz from objects smaller than 2 kilometers? Never recorded before in 60 years of cometary radio astronomy. Multiply those probabilities, you arrive at less than 1 in 4 million. 3 observatories failed because 3I Atlas reflects sunlight unusually, saturating sensors. This would explain calibration issues. The problem is that instrumental saturation produces uniform maximum readings, not rhythmic oscillations. Saturated digital cameras show constant white pixels, not blinking every 37 minutes. An instrumental error does not explain the trajectory deviations confirmed by independent optical observations made by amateur astronomers in Australia and South Africa using 40-centimeter telescopes. These home-built systems, with 2000s-era CCD technology, also captured the same micrometric corrections, discarded. These gases could create jets invisible in the optical range, but detectable in the infrared, explaining the trajectory adjustments. The James Webb Space Telescope did exactly that with other comets in 2024, revealing CO plumes, invisible to ground-based telescopes. But continuous outgassing would produce gradual and consistent acceleration, not periodic corrections every 5.2 hours. And even exotic outgassing does not generate coherent radio signals. Sublimating methane does not create natural lasers. This hypothesis covers 1 anomaly, ignoring 2. Are not periodic corrections every 5.2 hours. And even exotic outgassing doesn't generate coherent radio signals. Sublimating methane doesn't create natural lasers. This hypothesis covers 1 anomaly, but ignores 2. Perhaps the nucleus of 3I Atlas contains unusual concentrations of iron, nickel, or ferromagnetic minerals that, by interacting with the interplanetary magnetic field of the solar wind, produce sufficient Lorentz forces to slightly alter its trajectory. Metallic asteroids like Psyche, which NASA plans to visit in 2029, have up to 90% iron by mass. But even Psyche, with a diameter of 280 kilometers and a mass a billion times greater than 3I Atlas, doesn't exhibit detectable deviations due to magnetic interaction. The Lorentz force on small objects is negligible compared to solar gravity. You would need its own planetary strength magnetic field, something icy comets simply don't possess. Models indicate this explanation fails by 6 orders of magnitude. So cautious alternatives begin to emerge, those that scientists mention in private conversations but rarely publish. First possibility, 3I Atlas could carry rare piezoelectric minerals. Piezoelectricity is the phenomenon where certain crystals generate voltage when subjected to mechanical pressure. Quartz does this, as do tourmaline and topaz. If the comet's nucleus has internal cavities filled with specific crystalline formations, and if solar radiation causes differential thermal expansion, it could, in theory, generate electrical oscillations. These oscillations, interacting with ionized plasma around the comet, might produce modulated radio emissions. The key word here is perhaps. No laboratory experiment has ever demonstrated natural piezoelectricity generating coherent radio signals in space conditions. It would be an unprecedented phenomenon, requiring very specific internal geometries. That would be irresponsible without definitive data. But consider the possibility of a technological fossil, a degraded remnant of some civilization that existed and went extinct millions or billions of years ago. Think about what the Voyager 1 probe, launched in 1977, will look like 10 million years from now. An irregular rock covered in interstellar ice, but with internal metallic cavities, resonators, geometric structures that could interact strangely with radiation. It wouldn't function as active technology anymore, but its residual geometries could produce anomalous physical effects when exposed to specific conditions. Is it plausible? Depending on how many technological civilizations arose and died in the galaxy before us, such objects could be drifting in interstellar space in numbers we simply never calculated. Depending on how many technological civilizations arose and died in the galaxy before us, such objects could be drifting in interstellar space in numbers we simply never accounted for. In 2017, Oumuamua accelerated as it left the solar system without showing cometary jets, leading Avi Loeb, a Harvard astronomer, to publicly suggest it could be an artificial solar sail, a remnant of alien technology. The scientific community largely rejected the idea, attributing the acceleration to outgassing of invisible molecular hydrogen. But Loeb is no crackpot. He has published over 700 peer-reviewed papers. His basic argument was simple. When you eliminate the impossible and what remains is the improbable deserves investigation. 3I Atlas presents more numerous and better documented anomalies than Oumuamua. If 3 independent systems failed because the object emits something our sensors were not designed to ignore, we need to ask what that something is. The Transient Object. Coordinating Agency, ACOT, is an international consortium responsible for validating astronomical discoveries before official publication. When observatories report something strange, ACOT convenes a review panel to check for data reduction errors, software bugs, or biased interpretations. This process normally takes 48 to 72 hours. But ACOT halted the review of 3I Atlas data on October 19th, and, as of the scripting of this video, has yet to release approval for publication in scientific journals. The official justification mentions methodological inconsistencies, but the normal protocol would be to specifically point out which inconsistencies, allowing observatories to correct and resubmit. Instead, silence. The Southern Optical Consortium, frustrated by the delay, released partial telemetry on October 18th via a public raw data portal. Technically legal, but politically risky. Unreviewed data can contain errors that, if disclosed, tarnish the observatory's reputation. But they preferred the risk over opacity. The Andean Radio Observatory and the Pacific Infrared Detection Institute, on the other hand, chose to await ACOT's approval, meaning their full data remains inaccessible. Transparency versus protocol. The tension is palpable in academic mailing lists, where astronomers debate what to do when the review system freezes. But the practical effect is that the observation window is closing. 3I Atlas's perihelion, its closest point to the Sun, occurs on October 28th. After this date, the object will begin to plunge back into interstellar space, accelerating as solar gravity slingshots it beyond Jupiter's orbit. In less than 4 weeks, it will be over 7.5 astronomical units, approximately 1.1 billion kilometers away, out of reach for most terrestrial telescopes. Only the largest instruments, such as the Very Large Telescope in Chile or Keck in Hawaii, would still be able to detect it, and even then, only as a point of light too faint for detailed spectroscopy. Even the largest instruments, like the Very Large Telescope in Chile or Keck in Hawaii, would still be able to detect it, and even then, only as a point of light too faint for detailed spectroscopy. If 3I Atlas confirms an exotic composition with rare piezoelectric minerals, we learn that interstellar chemistry is more diverse than we've modeled, opening possibilities for planetary formation outside current paradigms. This rewrites textbooks, but keeps the universe safe and comprehensible. If the anomalies persist without a convincing natural explanation, and if additional high-resolution spectroscopy or planetary radar data reveal internal geometries inconsistent with geological formation, then we face the hypothesis of degraded artificiality. That doesn't just rewrite textbooks, it rewrites the history of the galaxy. But if we don't collect this data in the next 2 weeks, the opportunity vanishes for decades until another interstellar visitor crosses the solar system. First, emergency international coordination. Telescopes on 3 continents need to point at 3I Atlas continuously, collecting spectra in optical, near-infrared, ultraviolet, and radio wavelengths. The Atacama Large Millimeter Array in Chile, which operates at wavelengths between infrared and radio, could map the core's temperature with sufficient angular resolution to detect hotspots or internal structures. This was done with Oumuamua in a limited way, but with 3I Atlas we have an advantage. It's still relatively close and bright. Planetary radar is the definitive tool. The Arecibo system was destroyed in 2020, but Goldstone in California and Greenbank in West Virginia still operate radars capable of illuminating objects up to 0.5 astronomical units. 3A Atlas passes within this distance between October 24 and 30. Radar returns three-dimensional shape, surface roughness, and even internal structures if there's a density contrast. A single high-power radar ping could resolve the question of natural geometry versus artifice in hours. Each session costs tens of thousands of dollars in antenna time and requires approval from committees that evaluate scientific priorities. Potentially hazardous asteroids always take precedence because the issue is direct planetary defense. 3I Atlas does not threaten collision with Earth. Its hyperbolic trajectory guarantees it will never return. To secure radar time, astronomers need to argue that the anomalies justify the cost and urgency. Herein lies the political impasse. If you publicly claim an object might have artificial geometries and then radar shows only ordinary rock, your academic credibility melts away. If you underestimate the anomalies and miss the chance to confirm something extraordinary, history will judge you for the rest of your career. Scientists are human. The incentive pushes for excessive caution. There's also the ambitious plan, an intercept mission. The European Space Agency maintains a rapid mission concept called Comet Interceptor, designed to be launched towards an interstellar comet with less than 6 months warning. The idea is to have the probe already in space in a waiting orbit and activate its thrusters when an interesting target appears. But Comet Interceptor is still under development, with a launch planned for 2029. For 3I Atlas, a dedicated mission launched in weeks would be required, technically unfeasible with conventional rockets. The only realistic alternative would be a flyby mission using a fast launcher, like Falcon Heavy or Ariane 6, carrying a high-resolution camera and a mass spectrometer. Even so, achieving 91 kilometers per second relative velocity demands a gravity-assisted trajectory, which is complex to plan in less than 20 days. To reach 3I Atlas before perihelion, a probe would require an absurd delta-V, burning tons of propellant and carrying only minimalist instruments. Alternatively, you wait for the object to move away, launch a heavier and well-equipped mission, but accept that it will be so distant that the encounter will last minutes with inferior resolution. International coordination would help, dividing costs among NASA, ESA, JAXA, and Chinese agencies, but such agreements take months to negotiate, time that 3I Atlas does not afford us. So the question boils down to choices. Do we accept that this object will pass without definitive answers, becoming another astronomical mystery debated at conferences for the next 20 years? Or do we mobilize exceptional resources, risking credibility and budgets because the anomaly suggests something that transcends academic curiosity? The scientific community is divided, not for lack of interest, but due to an excess of institutional caution. Harvard's Avi Loeb has publicly called for private funds to finance at least one intensive radar campaign. Other astronomers argue that existing data has not yet exhausted natural explanations, and that acting prematurely wastes resources better used in confirmed science. Meanwhile, 3I Atlas approaches perihelion, indifferent to human debate. On October 28th, it will be 1.8 astronomical units from the Sun, about 270 million kilometers, shining with an apparent magnitude close to 12, visible in 20-centimeter amateur telescopes under dark skies. Observers in the southern hemisphere will have an advantage, with the object high in the sky during the pre-dawn hours. If thermal oscillations continue, infrared telescopes should capture the 37-minute cycles with even greater clarity. If trajectory deviations persist, ephemerides will require daily corrections. If radio emissions intensify as the comet approaches the Sun and interacts with a higher density of solar wind, radio telescopes will have the best opportunity to characterize the bandwidth and verify if there is modulation or an internal pattern in the signal. As it approaches the Sun and interacts with a denser solar wind, radio telescopes will have the best opportunity to characterize its bandwidth, checking for modulation or internal patterns in the signal. Confirmation of an exotic natural cause would be reassuring but humbling, reminding us that the universe still holds chemistry and physics we don't yet predict. Confirmation of artificial geometry, even degraded, collapses paradigms. It would demonstrate that technology can persist for geological ages in interstellar space, that advanced civilizations may have arisen and disappeared billions of years before us, leaving technological fossils drifting in the galaxy like bottles in a cosmic ocean. This second possibility demands intellectual humility, to accept that perhaps we are neither the first nor the last, merely another attempt in a long series of consciousnesses that ascend, explore, and eventually become extinct. Or perhaps 3I Atlas is just a strange comet with properties that will force cometary formation models to include new parameters. Perhaps in March 2026, when all data is reviewed, published, and replicated, some doctoral student at Leiden University will discover that graphite crystals aligned in an interstellar magnetic field produce precisely these anomalies under specific conditions. And we will laugh at the hysteria, file 3i Atlas away as an interesting footnote, and continue mapping the galaxy with renewed confidence that we understand the rules. 3 independent observatories still cannot explain why their instruments failed simultaneously. Peer review is frozen for reasons not entirely clear, and an object crossing the solar system at record speed carries signatures that defy 60 years of cometary science. If this is the moment we confirm just another exotic natural phenomenon, we will learn something valuable about interstellar chemistry. If it is the moment we find tangible evidence of ancient artificiality, then we are living through the most significant discovery in human history, and we are not sure if we are ready to accept it. Mass instrumental coincidence? Exotic chemistry we haven't modeled? Or something that forces us to look at the night sky with different eyes? Leave your opinion in the comments, subscribe to follow developments, and share this video with anyone who deserves to know that sometimes the universe sends us questions before giving us answers. Either we confirm peculiar chemistry, or we open up the possibility that out there, lost in the abyss between stars, drift the remnants of those who tried before us. And perhaps, just perhaps, one of those attempts has just passed by, carrying a whisper that our instruments barely know how to listen to. A whisper of 1420 megahertz, too narrow to be an accident, too precise to be forgotten.